Okay, hello everyone. Yes, so today is the first video in a series of videos which I plan to make on matching theory. So I plan to discuss some of the lesser known results of matching theory. Okay, so the goal is to discuss in a simplified way. Okay, discuss some lesser known results, more maybe some will be more contemporary, some will be slightly older, but the lesser known uh, results in, I should not just say matching theory, but maybe stable matching theory. Stable matching theory. Okay, so what is it that I'm going to do? Okay, and why am I doing this? Okay, so what I'm going to do is basically review some. So I'll be discussing some results in stable matching theory from papers, from certain papers. So some of the lesser known results, which I find available only in some research papers, and they are very densely packed sometimes, and sometimes there is just like a lot of notations and is densely packed and maybe lacks motivation, or you know the more newer people who are interested in this topic find it hard to penetrate. Okay, so myself have experienced that. So I will try to make it less dense, try to simplify, add some motivations. Okay, and maybe if I have some insights of my own, I will try to bring them. Okay, so these results will be some from some papers which we will see. And obviously why I'm doing this is because I find that this is missing. Yeah, discussions on the lesser known results of matching theory, for example, certain properties of the Gale-Shapley algorithm, like it gives man optimal, or discussing the lattice structure, or uh, other kinds of instances where you have ties or where you have incomplete lists, algorithms in those situations and such. I find that these are not available. Now, obviously on YouTube, we have at least maybe 100 videos on the Gale-Shapley algorithm, but then maybe zero on its extension that is used to discuss that's super stable matching or strongly stable matchings. So I'll try to present them. Okay. So let's get started with what we're going to do, what I plan to do today. So for today, right? So today I plan to discuss the following paper. So maybe I'll just first share the screen of that for a second so that you can see it first. So this is the paper. It's by Robert Irving. So this guy is very well known in this area of stable matchings. And we are going to discuss stable marriage, where we have lists and the lists have indifferences. Okay. And first we're going to describe the problem, and then we will say. Okay. So let's come to the. So this is the paper. This paper is just freely available. You can download it by Googling this. But I want to simplify simplify one of the theorems of this paper. Okay, so that's the goal. Yeah. So let me be more precise. Right. So to say it more precisely, I plan to discuss the algorithm for finding super stable matching. I'll obviously define what these things mean. Okay. Super stable matching. Okay, so that is the context. So how does, first of all, what is this notion of super stable matching? How does it come about? So initially the context is that there are n men, okay, and they have n men and women as usual. This is just the language that we use. Women, and you have complete preference lists The preference list, each man has a preference list, each woman has a preference list. This you would know. This is the basic setup of the first stable matching problem, right? So complete preference list. But now there are ties. I should just say complete preference list with ties. Okay, so this is the context. This is the setup. You have n men, n women, and you have each man has a list, each woman has a list, and the preferences are complete, and then there are ties. So first of all, we want to define a notion of stability. Okay, define a notion of stability. I mean, it's already defined. I'm just going to say the definition, obviously. Define a notion of stability in this situation. And with that in mind, I'll just say define a notion of stability for a matching. Under this circumstance. Yeah. So in the usual setup, what's the definition of stable? So in the usual setup, in the setup with no ties, what's the definition of a stable matching? We know this. In this situation, the definition is that there is no pair, no man and woman, no pair M comma W, okay, such that let's call this M. Yeah, no pair M comma W such that M and W prefer each other to their current partners. Current partners means that in that matching. So in a matching M, we shouldn't have a pair M comma W where M and W prefer each other to their current partner. So this all of us know, right? This kind of pair should not be present in a matching. Then we call that matching stable. Now, obviously, we all of us know this. I mean, yeah, if you have seen the first matching problems, then you know this. But now that there are indifferences or there are ties or indifferences, then how can we extend this definition? Okay, so in this case, we make an extension as follows. Okay. Just first of all, obviously, this kind of pair that we have written here should not be present. That's certainly true, right? We don't want this. We don't want this kind of pair. And also what we don't want or M and W are indifferent to each other with respect to their current partners. Now, what does this mean? We'll have to add another condition, but so let's say that this is M and then this is W, and let's say this is W prime, and this is M prime. Okay. Now, if in the matching M is matched with W prime, and M prime is matched with W, okay, then we do not want the following situation. Okay, we do not want that. We don't want that M prefers W, or M is indifferent, or it's tied. M is indifferent between W prime and W. We don't want M to be indifferent between W prime and W. Okay. And same for W. Yeah. So we don't want this. So if this is thing, then we don't want M to be indifferent between W prime and W, and also W to be indifferent between M and M prime. Okay. If this is a situation, then there is some intuition that this is also some kind of instability. Okay, though it depends on the context, it depends on what is the goal, what we are trying to model, and so on. But we call this an instability. Okay, so we do not want this. What we also don't want, maybe I will write that this side. What we also don't want is this. So I don't want is this, that let's say example M. So for M, W and W prime means M is indifferent to between his current partner and W benefits by from leaving. Then obviously this will also, we'll call this also unstable. Let me write that W prefers, so for W, M is better. Okay, so even if one person gets better off by leaving his current or her current partner, and the other one does not lose anything, is indifferent, then this is also unstable. Okay, so obviously if both M and W, so the first situation was if both M and W benefit from leaving their current partners, then that's obviously unstable. Even if one of them benefit from leaving their current partners and the other does not lose anything, then also it's unstable. Or if both don't lose anything, then also it is stable. Okay, so it's a very harsh condition. Okay, so then also it's unstable. So it's a very harsh condition in the sense that for such a matching to be stable, a lot of conditions have to be satisfied, right? Like there should not be any blocking pair in even the vaguest sense of blocking pair. That is the idea. Okay, so now that we have the three different kinds of blocking pairs, sort of, right? Blocking pair means M comma W, which can create a prop, which can create some sorts of instability. Okay, we understand them. Now we can just put it in the definition. So yeah, so let's now write a crisp definition so that we can work with it. Define a notion of stability. So here we will call a super stable. This means a matching that doesn't have the kind of instabilities we defined, doesn't have any of them, is called a super stable matching. So let's define that. Okay, super stable matching. So obviously it's a matching M. Okay, M is called super stable. Okay? M is, so obviously M is super stable is already written. M has, okay, not M, sorry, yeah, super stable, I'm just messing up a little bit. So superstable matching M. Okay. There is no M comma W, no pair M comma W such that the notations. The notations that I can use, I just want to keep it simple. 1 minute. Yeah. So that there are 3 conditions, right? The 3 kinds of blocking pairs, and all 3 we want to avoid. So we have to write it in full. Okay. Usually this is presented by starting from weakly stable, strongly stable, and then kind of grows to that. So it's an addition one by one, but right now, since we are doing it just from the beginning, super stable, so let me just put it like that. So first, we don't want. So can I use a graphical? Let's use a graphical one only. Okay. So we don't want this M comma W such that now this obviously you understand this just bold one obviously means the edges which are in the matching. Okay. The situation we don't want the following situation where now M and W can both benefit. So for M, W is higher than W prime, and so you understand this notation can be useful for for W. So this will be M prime. Now for W, we don't want both of them to become happier, right? Otherwise we would rather have this intuitively, but this is the definition. Okay. And what we also don't want, I mean, I can just put it here. Yeah, so just the setup, I can just put them here. 1, there is no M comma W such that this happens, or if one of them benefits and the other doesn't lose anything, which can be written as for M, he is indifferent between W prime and W, and for W, there is a benefit. Okay. I mean, so then we'll get 4 conditions. I mean, you can have a symmetric thing with M, W, where W doesn't lose anything. W is tied between her current partner and M benefits. So we don't want this also. And also the 4th one, which is probably sounds a little too restrictive, but it is there for a reason. Maybe I'll try to say a certain context in which superstable matchings is the right notion to consider. Let's see. So first, let's get the definitions out of the way. And then the 4th condition is if both don't lose anything, then also. So maybe this super stable is like completely stable, solid. If something ends up being super stable, it's like just solid, stable. Like there's no vibration, also completely stable in that sense. Okay. M, and then there is W and W prime. So both are indifferent, or one of them benefits and the other obviously doesn't lose, then, or if both benefit, then obviously we don't want such pairs at all. So this is the definition. So this is the clear definition of super stable. This is the first thing. So let's move to the, let's keep the definitions here and let's move to the, yeah, I mean, I think it's good to just get some intuition for these things before we move into the algorithm. Of some of us may know the definitions very well and have the sense and so on. So then this portion can be skipped then, but let me do it so that it's a good. So really the question that I'm asking here is, why super stable? Why do you want such these 4 conditions? Okay. So, well, the idea is that start with preference list with no ties. Start with preference list with no ties. Let's say there are no ties. Okay. Let's say there are three people and we have the normal preference list. You could shuffle them or not. And similarly for the women. So this obviously means that W1 is the highest preferred, W2 is the next one, and W3 is the least. So let's say that this preference list, and these is being sent from one place to the other. So second thing that's happening is being transported. So this reference list is being transported and errors occur. Okay. Now, what do I mean by errors occur? What kind of errors am I talking about? Okay. By errors occurring means that, I mean, let's say this preference list goes, and somehow W1 and W2 become indistinguishable. So like W2 doesn't become less than W1, but they get tied. Okay. And similarly, while just this transportation, whatever medium, whatever, but the point is, yeah, or you don't know the full truth. You could keep it like that also, right? That in actuality, this doesn't have any ties, but people are not willing to tell the complete truth. They're not willing to lie, but they're not willing to tell the complete truth. So in those situations also, you do end up, so what you end up having access to is maybe something like this, where this gets tied. So you have access to this, but in actuality, there was a complete list. Okay. And now you want to, now the goal is to come up with a matching. Goal is to make a stable matching. You want to make a stable matching with the given information that we have access to. Okay, such that, let's say M, stable matching M, such that M remains stable, okay, in the original list. Now this looks tricky, isn't it? This looks like a very tricky question. Okay, I mean, I don't have access to the full information. I only have access to this list, which some kind of a some loss of information has happened. I shouldn't just say distortion because the order has not changed. Otherwise, you cannot really say with certainty. Okay? But some things have become tied. So it's like no one is lying, but they're kind of not telling the truth. Yeah, they're not willing to say, let's say M1 is not willing to say W1, W2, which is higher ranked. Okay, so he's not lying, but he's not telling the complete thing. So this is what you have access to. And now we want to design, with this information available to us, we want to design a matching which will work even in the original case. So how to do this? So this is where this notion of superstability comes in. Let's try to see that. Let me try to do it. So what is it that we can remove from here? We have to remove something. Yeah, let's remove these conditions, because you will see we'll arrive at these conditions once again. So let's remove these conditions, and let's try to do this. So we have this our goal. Think about, you can pause and think. So you can, right. So if I match mi with, let's say, wi, okay, and mj with wj, with the information that I have with the tied lists, if I'm matching, so let's, right. Okay, now if wi and wj are tied, I mean for mi, wi and wj are tied, okay, then potentially this creates no problems if you look at this list that we have access to. Okay. But when could it become a problem in the original list? So when could these edges end up, having a problem? Okay. So really the question is, when can miwj create problem in the original list? Yeah, when can that happen? So in mi's list, wi and wj, let's say these two are the only one, and they are tied for mi. So there is maybe no problem if you look at the tied list. But now if you go back to the original list, okay, and let's say that in the original list, if in the original list, let's just call this L, the original list L, if in L, if in actuality, mi prefers wj more than wi, okay, yeah, and I mean in the tied list situation itself, so let's keep it here, yep. And wj prefers, so wj prefers mj to mi, now mi to mj. So you have the situation where you have the tied version, and in that we have kind of created a matching, and this is just small, just small view of that. And if in this situation w and wj are tied, and mi, but wj prefers mi more, you see this is not, I mean, if you just look at stability in the weak sense, in just the normal sense, is this unstable in the normal sense? Would you call this unstable? No, because you would say, well, you'll see mi has nothing to gain, right, by deleting this and forming this h with wj. So there is no problem, you can say, right, there is no problem. But when you go to the original list, then it becomes a problem, right? Because in the original list, if mi prefers wj more and wj also already preferring mi more, that's not going to change. The order doesn't change, right? Because no one is lying. So, okay. Then, so we don't even need this and, that's already there. Then it's unstable. It's unstable. It's unstable with respect to the original list. Doesn't remain stable, right? This matching will not remain stable. You see, so that's why in the case in this situation of tied lists, we need more harsher conditions. Okay, we need more harsher condition, and that basically means that we need to call this a blocking pair. Means that this occurrence of this we need to avoid. So in our definition of stability, we need to say this doesn't occur, or it's a blocking pair. Okay, that's the point. We need to call this a blocking pair. And similarly, you know, both even if both are equal here, it could become a problem. You can work that out, right? It could become a problem in the original list. Yeah. So the point is that even if you're solely interested in preference lists with no ties, and you want to solve this problem of finding this stable matching, but if you are transporting and there's some errors occurring, then even if you just want a stable matching in the original list, or even if you want a stable matching in the original list, then you need to put this extra, maybe artificial looking conditions on stability, more restrictive conditions on stability in the in the tied case. Okay, so we need to add these extra conditions, and these basically form the basis for these form the definition of super stable. And so this leads to the notion of super stability. Okay, and think about it. Right. So in summary, if we try to summarize this, so initially we have n men and women, no ties, okay? And then due to some reason could be transporting some transfer, ties created. Okay, and then you, with this information, yeah, with this information, the goal was to make a matching M with this information such that when you look at M in the original case, it remains a good matching. Okay, so that M remains stable in original case. Okay, and you see this leads to the concept of the super stability. So this whole thing is basically leads to the concept of super stable matching, or basically the extra conditions we are forced to add, and that we just give a name to that. We call it super stable. So next, we'll not do this now, but next time we'll do. So now that we have the definitions clear, next time we'll go for the algorithm for super stable match. But we'll do it in a, as a way as like we are solving a problem, and we will try to, I'll try to do it in a way so that it seems, so that you will see that it is just an extension of the usual Gale-Shapley algorithm with the goal of trying to remove or trying to get rid of the blocking pairs, of the extra new type of blocking pairs. Okay, So we'll have to add some conditions in the known algorithm so that the extra blocking pairs are removed, and that will lead to an algorithm for the super stable matching. Okay, that's what we'll do next, and then we'll do the similar stuff for strongly stable matchings and uh, other things. Maybe we'll look at the lattice structure and so on. Okay, so yeah, so this was the first, just an intro into the plan. The plan is just to present these things so that it becomes more accessible to more people, and yeah, so the more people can get interested in this, because this is usually not present in books. These materials are not yet available. So yeah, let's see.